Hello guys, hello ma'am. Today we're gonna discuss about the chemistry of water treatment. Under this chemistry of water treatment, we have the water quality, coagulation, softening, mixing and flocculation, sedimentation, filtration, disinfection, adsorption membranes, water plant residuals, and management. The EPA has defined three types of public water systems. We have the community water system, non-community water system, and the transient non-community water system. So for the community water system, it is a public water system that supplies water to the same population year-round. Non-community water system is a public water system that regularly supplies water to at least 25 of the same people at least 6 months per year, but not year-round. Some examples are schools, factories, office buildings, and hospitals that have their own water system. Transient non-community water system is a public water system that provides water in a place such as a gas station or campground where people do not remain for a long period of time. Water quality. Precipitation in the form of rain, hail, or sleet contains very few impurities. It may contain trace amounts of mineral matter, gases, and other substances as it forms and falls through the Earth's atmosphere. The precipitation, however, has virtually no bacterial content. Once precipitation reaches the Earth's surface, many opportunities are presented for the introduction of mineral and organic substances, microorganisms, and other forms of pollution or contamination. When water runs over or through the ground surface, it may pick up particles of soil. It is noticeable in the water as cloudiness or turbidity. It also picks up a particle of organic matter and bacteria. As surface water seeps downward into the soil and through the underlying material to the water table. Most of the suspended particles are filtered out. This natural filtration may be partially effective in removing bacteria and other particulate material. There are four categories are used to describe drinking water quality. First, the physical characteristic, chemical, microbiological, and radiological. First, we're gonna talk about the physical characteristics. So under this characteristic, we have turbidity, color, taste and odor, and temperature. Turbidity, the presence of suspended materials such as clay, silt, finely divided organic material, plankton, and other particulate material in water is known as turbidity. Good lubog. The unit of measure is a turbidity unit or neplometric turbidity unit. It is determined by reference to a chemical mixture that produces a reproducible refraction of light. Turbidities in excess of 5 turbidity unit are easily detectable in a glass of water and are usually objectionable for aesthetic reasons. Diba usahay ka ng sa tubig ka ng limpyo nga bildo naman tayo makita nga maglutaw-lutaw mo na siya nga organic materials. Turbidity. Color. Dissolved organic material from decaying vegetation and certain inorganic matter cause color in water. Occasionally, excessive blooms of algae or growth of aquatic microorganisms may also impart color. White color itself is not usually objectionable from the standpoint of health. Its presence is aesthetically objectionable and suggests that the water needs appropriate treatment. So, dili ibig sabihin no nga tinaw ang tubig, limpyo, hugaw Japan. So, kailangan pa i-treat. Taste and odor. Taste and odor in water can be caused by foreign matter such as organic compounds, organic salt, and dissolved gases. These materials may come from domestic, agriculture, and natural resources. Temperature. The most desirable drinking waters are consistently cool and do not have temperature fluctuations of more than a few degrees. Groundwater and surface water from mountainous areas generally meet this criteria. So next is the chemical characteristics. Under these characteristics, we have the chloride, fluoride, iron, lead, manganese, sodium, sulfate, zinc, arsenic, toxic inorganic substances, and the toxic organic substances. Chloride. Chloride, most waters contain some chloride. The amount present can be caused by the leaching of marine sedimentary deposits or by pollution from seawater, brine, or industrial or domestic waste. Fluoride. In some areas, water sources contain natural fluoride, where the concentrations approach optimum levels. Beneficial health effects have been observed. Iron. Small amounts of iron frequently are present in water because of the large amount of iron in geologic materials. The presence of iron in water is considered objectionable because it imparts a brownish color to laundered goods and affects the taste of beverages such as tea and coffee. Lead. Exposure of the body to lead, however brief, can be seriously damaging to health. Prolonged exposure to relatively small quantities may result in serious illness or death. Lead taken into the body in quantities in excess of certain relatively low normal limits is a cumulative poison. Manganese. Manganese imparts a brownish color to water and to cloth that is washed in it. Flavors coffee and tea with a medicinal taste. Sodium. The presence of sodium in water can affect persons suffering from heart, kidney, or circulatory diseases or ailments. Sulfate. Waters containing high concentration of sulfate caused by leaching of natural deposits of magnesium sulfate, or what they call Epsom salts, or sodium sulfate, or Glaubert salt, may be undesirable because of their laxative effect. Zinc. Zinc is found in some natural waters, particularly in areas where zinc deposits have been mined. Zinc is not considered detrimental to health, but it will impart an undesirable taste to drinking water. Arsenic. Arsenic occurs naturally in the environment and is also widely used in timber treatment, agricultural, chemical, and manufacturing of gallium arsenide waters, glass, and alloys. Arsenic in drinking water is associated with lung and urinary bladder cancer. So, toxic inorganic substances, we have the antimony, arsenic, barium, beryllium, boron, cadmium, chlorine, chromium, and many more. The toxic organic substances. There are over 120 toxic organic compounds listed on the U.S. Environmental Protection Agency Priority Pollutant List. This includes pesticides, insecticides, and solvents. Like the inorganic substances, their effect may be acute or chronic. The next characteristic is the microbiological characteristics. Water for drinking and cooking purposes must be made free from disease-producing organisms or pathogens. These organisms include viruses, bacteria, protozoa, and worms. Some organisms which cause disease in people originate with fecal discharges of infected individuals. Others are from the fecal discharge of animals. The next characteristic is the radiological characteristic. The development and use of atomic energy as a power source and the mining of radioactive materials as well as naturally occurring radioactive materials have made it necessary to establish limiting concentration for intake into the body of radioactive substances, including drinking water. The effect of human exposure to radiation or radioactive materials are harmful, and any unnecessary exposure should be avoided. Humans have always been exposed to natural radiation from water, food, and air. Water classification by source. Potable water is most conveniently classified as to its source, that is, groundwater or surface water. Generally, groundwater is uncontaminated but may contain aesthetically or economically undesirable impurities. However, groundwaters can be influenced by man-made spills and become contaminated. Surface water must be considered to be contaminated with bacteria, viruses, or inorganic substances that could present a health hazard. Treatment systems. Treatment plants can be classified as simple disinfection, filter plants, or softening plants. Plants employing simple chlorination are usually groundwater sources that have high water quality and chlorinate to ensure that the water reaching customers contain safe bacteria levels. A groundwater source can contain naturally occurring contaminants such as arsenic, fluoride, radionuclides, iron, or manganese. In this case, the water may be treated by absorption, ion exchange, or precipitation processes to remove the contaminant. Groundwaters can also be contaminated by spills caused by humans. Infiltration plant, rapid mixing, flocculation, sedimentation, filtration, and disinfection are employed to remove color, turbidity, taste, and other organic matter and bacteria. So, coagulation. So, what is coagulation? Coagulation is a method to alter the colloids so that they will be able to approach and adhere to each other to form larger flock particles. The purpose of coagulation is to alter the colloids so that they can adhere to each other. During coagulation, a positive ion is added to water to reduce the surface charge to the point where the colloids are not repelled from each other. The object of coagulation is to turn the small particles of color, turbidity, and bacteria into larger flocks either as precipitates or suspended particles. These flocks are then conditioned so that they will be readily removed in subsequent process. Technically, coagulation applies to the removal of colloidal particles. Coagulation in this topic or chapter will refer to colloid removal only. We define coagulation as a method to alter the colloids so that they will be able to approach and adhere to each other to form larger flock particles. Colloid stability. For colloids to remain stable, they must remain small. Most colloids are stable because they possess a negative charge that repels other colloidal particles before they collide with one another. The colloids are continually involved in Brownian movement, which is merely random movement. Charges on colloids are measured by placing DC electrodes in colloidal dispersion. The particles migrate to the pole of opposite charge at a rate proportional to the potential gradient. Generally, the larger the surface charge, the more stable the suspension. Colloid destabilization. Colloids are stable because of their surface charge. In order to destabilize the particles, we must neutralize this charge. Such neutralization can take place by addition of ion of opposite charge to the colloid. Since most colloids found in water are negatively charged, the addition of sodium ions should reduce the charge. There are three key properties of a coagulant. First is the trivalent cation, the non-toxic, and the insoluble in the neutral pH range. The trivalent cation, as indicated in the last section, the colloids most commonly found in natural waters are negatively charged. Hence, the cation is required to neutralize the charge. Non-toxic. This requirement is obvious for the production of a safe water. Insoluble in neutral pH range. The coagulant that is added must precipitate out of solution so that high concentration of the ion are not left in the water. Such precipitation greatly assists the colloid removal process. Coagulant aids. The four basic types of coagulant aids are the pH adjusters, activated silica, clay, and polymers. Softening. The term hardness is used to characterize a water that does not lather well, cause a scum in the bathtub, and leaves hard, white, crusty deposits on coffee pots, tea kettles, and hot water heaters. The failure to lather well the information of scum on bathtubs is the result of reactions of calcium and magnesium with the soap. So, we have this range of hard water clarification. So, if it is 0 to 75 mg per liter, then the description is soft. If it is 75 to 100, then it is moderately hard. If it is 100 to 300, it is considered hard. If it is greater than 300, it is hard. Mixing and flocculation. Mixing or rapid mixing, as it is called, is the process whereby the chemicals are quickly and uniformly dispersed in the water. Ideally, and chemicals would be instantaneously dispersed throughout the water. During coagulation and softening, the chemical reactions that take place in rapid mixing from precipitates, either aluminum hydroxide or iron hydroxide, form during coagulation, while calcium carbonate and magnesium hydroxide from during softening. During coagulation and softening, the chemical reaction that take place in rapid mixing form precipitates. In the treatment of water and wastewater, the degree of mixing is measured by the velocity gradient, or G. The velocity gradient is best thought of as the amount of shear taking place. That is, the higher the G value, the more violent the mixing. Rapid mixing is probably the most important physical operation affecting coagulant, thus efficiency. The chemical reaction in coagulation is completed in less than 0.1 second. Therefore, it is imperative that mixing be as instantaneous and complete as possible. Flocculation. The objective of flocculation is to bring the particles into contact so that they will collide, stick together, and grow to a size that will readily settle. Enough mixing must be provided to bring the flux into contact and to keep the flux from settling in flocculation basin. Sedimentation. Particles will settle within a reasonable period of time can be removed in a sedimentation basin, also called a clarifier. Sedimentation basins are usually rectangular or circular, with either a radial or upward water flow pattern, regardless of the type of basin. There are four. This design can be divided into four zones. We have the inlet, settling, outlet, and sludge storage. The sedimentation concept. There are two important terms to understand in sedimentation zone design. The first is the particle or the flock settling velocity versus the second is the velocity at which the tank is designed to operate, called the overflow rate. Zones of sedimentation tank, di ba, giingon ako ganina tong inlet zone, settling zone, outlet zone, and sludge zone. Type 1 sedimentation is characterized particles that settle discretely at a constant settling velocity. They settle as individual particles and do not flocculate or stick to other particles during settling. Example of these particles are sand and grit materials. Generally speaking, the only application of type 1 settling is during pre-sedimentation for sand removal prior to coagulation in potable water plant and settling of sand particles during cleaning of rapid sand filters and in grit chambers. Type 2 sedimentation. Type 2 sedimentation is characterized by particles that flocculate during sedimentation. Because they flocculate, their size is constantly changing. Therefore, the settling velocity is changing. Generally, the settling velocity is increasing. These types of particles occur in aluminum or iron. Coagulation and primary sedimentation in settling tanks in trickling filtration. The type 3 sedimentation. In zone sedimentation, the particles are at high concentration, greater than 1000 mg per liter, such as the particles tend to settle as a mass and a distinct clear zone and sludge zone are present. Zone settling occurs in lime softening, sedimentation, activated sludge sedimentation, and sludge thickeners. Filtration. So, water filtration is a process of separating suspended or colloidal impurities from water by passage through a porous medium, usually a bed of sand or other medium. Water fills the pores or open spaces between the sand's particles, and the impurities are left behind, either clogged in open spaces or attached to the sand itself. Methods of classifying filters. According to the type of medium used, such as sand, coal, or what they call ancacrite, dual media, or what they call coal plus sand, or mixed media, which is mixed with coal, sand, and garnet. By allowable loading rate is the flow rate of water applied per unit area of the filter. It is the velocity of the water approaching the face of the filter. Three categories of human enteric pathogens are normally of consequence: bacteria, viruses, and amoebic cyst. Purposeful disinfection must be capable of destroying all three. Chlorine disinfecting action. Chlorine disinfection involves a very complex series of events and is influenced by the kind of and extent of reaction with the chlorine reactive materials, including nitrogen, temperature, pH, the variability of test organisms, and numerous other factors. Such factors greatly complicate attempts to determine the precise mode of action of chlorine on bacteria and other microorganisms. Disinfection. Disinfection is used in water treatment to reduce pathogens or disease-producing microorganisms to an acceptable level. Disinfection is not the same as sterilization. Sterilization implies the destruction of all living organisms. Drinking water need not to be sterile. To be practical service, such water disinfectants must possess the following properties. They must destroy the kinds of numbers of pathogens that may be introduced into water within a practicable period of time over an expected range in water temperature. Second, they must meet possible fluctuations in composition, concentration, and condition of waters or wastewater to be treated. Third, they must be neither toxic to humans and domestic animals nor unpalatable or otherwise objectionable in required concentration. Fourth, they must be dispensable at reasonable cost and safe and easy to store, transport, handle, and apply. Their strength, fifth, their strength or concentration in the treated water must be determined easily, quickly, and preferably automatically. 6. They must persist within disinfected water in a sufficient concentration to provide reasonable residual protection against its possible recontamination because this is not normally attainable property. The disappearance of residuals must be a warning that recontamination may have taken place. Chlorine reactions in water. Chlorine is the most common disinfecting chemical used. The term chlorination is often used synonymously used with disinfection. Chlorine may be used as the element as sodium hypochlorite or as calcium hypochlorite. When chlorine is added to water, a mixture of hydrochlorous acid and hydrochloric acid is formed. Chlorine or in an ammonia reactions. The reactions of chlorine with ammonia are of great significance in water chlorination process. When chlorine is added to water that contains natural or added ammonia, the ammonia reacts with HOCI to form various chloramines, which like HOCl retain the oxidizing power of chlorine. Practices of water chlorination. Evolution. Early water chlorination practices variously termed plain chlorination, simple chlorination, and marginal chlorination were applied for the purpose of disinfection. Chlorine ammonia treatment was soon thereafter introduced to limit the development of objectionable tastes and odors often associated with marginal chlorine disinfection. Combined residual chlorination. Combined residual chlorination practice involves the application of chlorine to water in order to produce with natural or added ammonia a combined available chlorine residual and to maintain that residual through part or all of a water treatment plant or distribution system. Free residual chlorination. Free residual chlorination practice involves the application of chlorine to water to produce either directly or through the destruction of ammonia a free available chlorine residual and to maintain the residual through part or all of a water treatment plant or distribution system. Free available chlorine form have higher oxidation potentials than combined available chlorine forms and therefore are more effective as oxidants. Chlorine dioxide. Another very strong oxidant is chlorine dioxide. Chlorine dioxide is formed on site by combining chlorine and sodium chloride. Chlorine dioxide is often used as a primary disinfectant in activating bacteria and yeast, followed by the use of chloramine as a distribution system. Disinfectant. Dioxide does not maintain a residual long enough to be useful as a distribution system disinfectant. Thus, the advantage of chlorine dioxide over chlorine is that chlorine dioxide does not react with precursors to form DBPs. Ozonation. Ozone is a pungent smelling unstable gas. It's a form of oxygen in which three atoms of oxygen are combined to form the molecule O3. Because of its instability, it is generated at the point of use. The ozone generating apparatus commonly is a discharge electrode. To reduce corrosion of generating apparatus, air is passed through a drying process and then into the ozone generator. The generator consists of two plates or a wire and a tube with an electric potential of 15,000 to 20,000 volts. The oxygen in the air is dissipated by the impact of electrons from the discharge electrode. Advanced oxidation processes, or AOPs, small letter S, are combination of disinfectants designed to produce hydroxyl radicals. Hydroxyl radicals are highly reactive, non-selective oxidants able to decompose many organic compounds. Most noteworthy of AOP process is ozone plus hydrogen peroxide. Adsorption. Adsorption is a mass transfer process wherein a substance is transferred from the liquid phase to the surface of a solid where it is bound by chemical or physical forces. Generally, in water treatment, the absorbent is activated carbon, either granular or powdered. PAC is fed to the raw water in a slurry and is generally used to remove taste and odor causing substances or to provide some removal or synthetic organic chemicals or SOC small letter S. The GAC is added to the existing filter system by replacing the antacryte with GAC, or an additional contactor is built and displaced in the flow scheme after primary filtration. The design of the GAC contactor is very similar to a filter box, although deeper. Membranes. So, membrane is a thin layer of material that is capable of separating materials as a function of their physical and chemical properties when a driving force is applied across the membrane. In the case of water treatment, the driving force is applied by using a high pressure pump and the membrane type is selected based on the constituents to be removed. Water plant residuals management. The precipitated chemicals and other materials removed from raw water to make it potable and palatable are termed residuals. Satisfactory treatment and disposal of water treatment plant residuals can be the single most complex and costly operation in the plant. Residuals withdrawn from coagulation and softening plants are composed largely of water, and residuals are often referred to as sludge. As much as 98% of the sludge mass may be water. Thus, for example, 20 kg of solid chemical precipitate is accompanied by 980 kg of water. Assuming equal densities for the precipitate and water, approximately 1 meter cube of sludge is produced for each 20 kg of chemicals added to the water. For even a small plant, let's say it is 0.05 meter cube per second. This might mean up to 800 meter cube of sludge, a substantial volume to say the least. Water treatment plants and the residuals they produce can be broadly divided into four general categories. First are those treatment plants that coagulate, filter, and oxidize surface water for removal of turbidity, color, bacteria, algae, some organic compounds, and often iron and or manganese. These plants generally use aluminum or iron salts or coagulation and produce two-way streams. The second type of treatment plants are those that practice softening for the removal of calcium and magnesium by the addition of lime, sodium hydroxide, and or soda ash. These plants produce clarifier basin sludges. The third type of plants are those that are designed to specifically remove trace inorganics such as nitrate, fluoride, radium, arsenic, and so forth. These plants use processes such as ion exchange, reverse osmosis, or adsorption. They produce liquid residuals or solid residuals such as spent adsorption material. The fourth category of treatment plants are those that produce air paste, residuals during the stripping of volatile compounds. The major types of treatment plants residual produced are shown in Table 6 to 19. Because 95% of the residuals produced are coagulants or softening sludge, they will be stressed in this section. Major treatment plants residuals: solid and liquid residuals. First, alum sludges. Number 2, iron sludges. 3, polymeric sludges. 4, softening sludges. Number 5 is the SFBW. 6, spent GAC or discharge from carbon systems. 7, slow sand filter cleanings. 8, residuals from iron and manganese removal plants. 9, spent pre-coat filter media. 10, ion exchange regenerant brine. 11, regenerant from activated alumina. 12, reverse osmosis reject gas phase residuals. 13, air stripping of gases. The most logical sludge management program attempts to use the following approach in disposing of the sludge. First is the minimization of sludge generation. Second, the chemical recovery of precipitates. Third, sludge treatment to reduce volume. Fourth, ultimate disposal in an environmentally safe manner. Sludge production and characteristics. In water treatment plants, sludge is most commonly produced in the following treatment processes: the pre-sedimentation, sedimentation, and filtration. Pre-sedimentation. Pre-sedimentation, when surface waters are withdrawn from watercourses that contain a large quantity of suspended materials. Pre-sedimentation prior to coagulation may be practiced. The purpose of this is to reduce the accumulation of solids in subsequent units. The settled material generally consists of fine sand, silt, clays, and organic decomposition products. Softening sedimentation basin. The residues of softening by precipitation with lime and soda ash will vary from a nearly pure chemical to a highly variable mixture. The softening process discussed earlier in this chapter produces a sludge containing primarily CaCO3 and MgOH2. Coagulation sedimentation basin. Aluminum or iron salts are generally used to accomplish coagulation. Or the chemistry of the two salts was discussed earlier in this chapter. The pH range of 6 to 8 is where the most water treatment plants effect the coagulation process. Minimization of Minimization of sludge generation for sustainability. Minimizing sludge generation can have an advantageous effect on the requirements and economics of handling, treating, and disposing of water treatment plant sludges. Minimization also results in the conservation of raw materials, energy, and labor. There are three methods to minimize the quantity of metal hydroxide precipitates in the sludge. First, changing the water treatment process to direct filtration. Second, substituting other coagulants and in particular using polymers that are more effective at lower dosage. 3. Third is conserving chemicals by determining optimum dosage at frequent intervals as raw water characteristics change. Sludge treatment. The treatment of solid and liquid waste produced in water treatment processes involves the separation of the water from the solid constituents, the degree necessary for the selected disposal method. Therefore, the required degree of treatment is a direct function of the ultimate disposal method. Sun drying beds. Sun drying beds operate on the simple principle of spreading the sludge out and letting it dry. As much as possible is removed by drainage or decant, and the rest of the water must have evaporate until the desired final solids concentration is reached. Sun drying beds have been built simply by cleaning an area of land, dumping the sludge, and hoping something happens. Freeze treatment. Dewatering sludge by either of the non-mechanical methods may be enhanced by physical conditioning of the sludge through alternate natural freezing and thawing cycles. The freeze-thaw process dehydrates the sludge particles by freezing the water that is closely associated with the particles. The dewatering process takes place in two stages. The first stage reduces sludge volume by selective freezing the water molecules. Next, the solids are dehydrated when they become freeze. Centrifuging. A centrifuge uses centrifugal force to speed up the separation of sludge particles from the liquid. In a typical unit, sludge is pumped into a horizontal cylindrical bowl rotating at 800 to 2000 revolutions per minute. Polymers used to sludge conditioning also are injected into the centrifuge. The solids are spun to the outside of the bowl where they are scraped out by screw conveyor. The liquid of centrate is returned to the treatment plant. Two types of centrifuges are currently used for sludge dewatering: the solid bowl and the basket bowl. For dewatering water treatment plant sludges, the solid bowl has proven to be more successful than the basket bowl. Centrifuges are very sensitive to changes in the concentration or composition of the sludge, as well as the amount of polymer applied. Vacuum filtration. A vacuum filter consists of cylindrical drum covered with a filtering material or fabric which rotates partially submerged in a vat of conditioned sludge. A vacuum is applied inside the drum to extract water, leaving the solids or filter cake on the filter medium. As the drum completes its rotational cycles, a blade scrapes the filter cake from the filter and the cycle begins again. Continuous belt filter press. The belt filter press operates on the principle that bending a sludge cake contained between two filter belts around a roll introduces shear and compressive forces in the cake, allowing water to work its way to the surface and out of the cake, thereby reducing the cake moisture content. Plate pressure filters. The basic component of a plate filter is series of resist vertical plates. Each plate is covered with cloth to support and contain the sludge cake. The plates are mounted in a frame consisting of two head supports connected by two horizontal parallel bars. Ultimate disposal. After all possible sludge treatment has been accomplished, a residual sludge remains, which must be sent to ultimate disposal or used in a beneficial manner. Of the many theoretical alternatives for ultimate disposal, only three are of practical interest. First is the co-disposal with sewage sludge. Second is the land filling or filing. Three is the beneficial use. That's all. Thank you.